Hello everyone, my name is Dharamveer Kumar. I am a PhD student at IIT Bombay, and today we'll be solving assignment 5. Yeah, just one second. Just one second. Yeah, sorry for that. So yeah, today I'll be solving assignment 5, and if you have any questions, let me know. I'll try to solve them. Kartike, are you saying something? You are audible, but the noise is... Hello, can you speak again? A bit loudly. Yeah, now it's okay, yeah. So do you have any questions? Is it assignment 5 or 4? Okay, in 7, okay. So let's first do 5. Let's clarify that and then I'll answer at the end, okay? Let me check if it's recording or not. Yeah, it's recording. Okay. Let's do this. This is a question. It's a little big question, but I'll try to solve this. So the question is: let f from R to R be a function. Now consider following statement. That means these following statements are true. Okay. The first one is that f is continuous. Second one is f inverse of u is open. So these are true statements about the function. So for every open okay, so all these statements are given. Okay, are they equivalent or not? That is the question. The question is so then A, B, C are equivalent because the definition of this thing, right? Second one is the definition of continuity in higher dimension, but that is not what we have taught. We have been taught, right? We have been taught the epsilon delta definition. So we have to basically show that the epsilon delta definition and the open set definition both are the same. Okay? So we'll do it properly, rigorously. A, B are equivalent, but C does not imply A. What does B and C are equivalent means? Something like this. Okay? So whenever we say something is equivalent, this is the true statement. I'll prove it. Okay? So first let's start with, so whenever there are like something like this, right? if you show like A, B, C, right? So if you show A, B, and if you show B implies C, that's it, you're done. Are you done? No. You have to imply like this is. You don't need C because by the implication B implies C. So this is what you have to do. Okay. So this is very simple. B and C are literally equivalent. Why? Because F inverse of, sorry, not inverse, pre-image. We have not shown that it is invertible. Okay. This is something I'm assuming you know this. Okay. I'll prove it. Maybe I'll prove this. Okay. So this is done. So now, if B is true, right? Let B be true. That means what? For every open set, F inverse U is open, right? So let A be any open set, or rather B is true, right? So let A be a closed set, any closed set. That implies RA is open this is from B, hence C. Similarly, the other way around. So what we have shown over here is that B is very simple. Now this statement, right? Let's prove this statement because these are the set, right? And this is true for not just open or close, any set. For any set A in R. Okay, just any set, doesn't have to be measurable, anything, any set, no properties of set, it just has to be a set. Okay, so now let's show this. Okay, so both are sets, right? We have to show both sets are equal. So let's start with let's start with showing this. Let me do like this. We'll first show and then we'll show okay. So let X be in F inverse RA. That implies, what does that imply? There exists a Y in RA such that f of x is equal to y. Right? We have to show that this x in fact belong to R minus F inverse. So this is a function, right? So just think of this. This is R. This is R. Okay, and then there is a set over here A, and then your Y belongs over here. Right, sorry, my bad. So what do we say F inverse of, so let's say X is in so F is going from here to here, right? So F inverse of RA, there is some point X, my bad, X is here, right? And what we're doing is we're taking it here. Such that there exists a Y in, this is A, right? There exists a Y somewhere over here. What is F pre-image of A? It will be someplace, it will be at some place, right? And we have to show that F inverse A, R minus F inverse A, basically our X is that. So there exists a Y in over A such that this is true, right? So now does Y belong to F inverse? You understand? This is not a, there is nothing about continuity, nothing. So what we have to say is, let's say F inverse of A, does Y belong over here? If not, if this is not the case, that implies Y belong to, sorry, my bad. So one second, yeah. So Y does not belong to A, right? That implies F of Y does not belong to F of A. Yeah, just one second, I'm a bit confused. Just one second. Yeah. Just one second. So this means X belongs to so X belongs to just think there is a mistake over here. So this is a complement, and let's say there is a point x over here. What can we say about x? Let A be in R. This is the definition of, yeah, but doing it after a long time, I'm a bit confused as well. Okay, so F inverse of RA is, if let X belongs to F inverse RA. So if X belongs to F inverse RA, that means X has to be someplace over here. Yeah. Yeah, I was. So if X belongs to F inverse RA, this implies that F of X belongs to RA. Right? So there must be a X over here which is going over here. Yeah. There must be X. So basically this is X someplace, at some place in R. Okay. Which is, there could be multiple X's, right? But so basically F inverse R of A is a set, right? So now if X belongs to F inverse R of A, that means there has to be an X somewhere in R such that F of X is going in R of A. Okay, this implies so F of X is in R minus A. Okay, so there is X, there is F of X over here. Now if there was a point in F inverse of A, let's call this X definitely does not belong to this case. Okay, it's simple to understand, right? So if F of X is in R of A, right, what does that mean about X? That X does not belong to F inverse of A. Because if X was in F inverse of A, that would imply what? Fx is in A, but Fx is in R of A. So hence x belong to R of inverse of. Okay, now this point. Okay, let x belong to R of f inverse of A. What does this mean? That x is outside this f inverse of A. Right? So now these are like equivalent statements. So what can we say about f of x? So this implies that f of x, so because x is not over here, f of x is in, and that implies that x is in. These are like these are like equivalent statements, and then we can show from there. This is what is important to show B double implies C. Now let's see 1 and 2, right? Sorry, A and B. Okay. Sorry for getting sidetracked a lot, but yeah, let's do. Just 1 second. By the way, I have not uploaded last week's YouTube video. I'll do that today only. Okay, so let's do the first and second one, and then we'll done with it. So we have to show now. First, let's do A implies B. What was A? That f is continuous. Now f is continuous. So what does it mean? And now, okay. So for let's do for open set. Let U be in open set. Be open. Okay. Now we have the epsilon delta definition, right? So now let x belong to f inverse of U. This implies that f of x is in U. Now since U is open, right, there exists an epsilon greater than 0 such that this ball, or rather I can draw an open set, f of x plus epsilon, f of x minus epsilon is contained in U. Now since f is continuous, there exists a delta greater than 0 such that So let's say this was an epsilon. For every epsilon, this is the case, right? Delta depends on epsilon. And it also depends on x as well. Since we are doing, okay. We have to show that F inverse U is open. That means, what does this mean? Why not? This implies, that implies, or we can write in other words, that for all y in but this was in U. So what does this imply? That y, for all y such that this is the case, y is in F inverse of U. Basically, so from here, just think that all y which is inside x minus delta and x plus delta, f of y is in U. Okay, so let's say if we draw a line, there is an x, right, and this is basically x minus delta and x plus delta, and all these y's are inside U. Okay, so what can we say from here? That this x minus delta and x plus delta is contained in F inverse of U. Right? This whole set is contained in F inverse of U. Because if you want to take the F of this whole thing is contained in, no matter which point you take. So what was x? X was some point in F inverse of U. So there was U over here. So U was an open set. There was some point over here. So we have this delta, which is a ball or an open interval, which is for no matter what x you choose, there is an open interval which is contained in F inverse of U. That implies F inverse of U is open. So that's how we prove 1 to 2. U was open, you have to show that F inverse U is open. You take a point to show that there is a ball around it or an open interval around it which is contained in F inverse of U itself. That's what we show. Okay. Now let's go from second to first. Okay. Or sorry, B to A. So that means F inverse of U is open for all open set U of R. Now this is there, right? and we have to show that f is continuous by our epsilon delta definition. Okay, so now consider, pick, you have to show continuity, so pick any x in R and epsilon greater than 0. It could be anything, right? So now x is definitely inside f inverse of f of x minus epsilon f of x so if I have a set, right, f of x needs to belong to this, obviously it belongs over here, right? Now we know that this is an open set, and f inverse of open set is an open set. That implies this is open from B. Okay, this is an open set, f inverse of open set is open set. So hence there exists a delta greater than 0 such that, because this lies inside open set, contained in right? So hence for all y inside this x minus delta and x plus delta, f of y belongs to this is the case. What does this mean? That for all y minus x less than delta implies f of y minus f of x. This is how you have to like do the proofs completely rigorously. So hence we have shown everything. Okay, now let's go to question 2. This is a simple one. Now, so you have defined f, basically is a parabola, or a simple quadratic equation. Okay. Now consider an interval AB. This is an interval for some which of the following is true. A, f inverse of AB is an open interval. So we already know that f of fx is equal to x square, right? It's continuous. So continuous function, interval, image of an interval will be an interval. Okay. No, sorry, function of an interval, if it's continuous, an interval, if you take f of interval is interval, not the inverse, sorry, my bad. Yeah. So and B is what f inverse of AB need not be an interval either open or closed interval. There are other intervals as well. Open interval, I have told you, right? And then D is f inverse of AB is either open or union of two open intervals. So either if it is an interval, it's an open interval, it's a union of two open intervals, or it's empty. So we have shown this is a continuous function, right? And this is definitely an open set. So f inverse of open is definitely an open set. It's at least an open set. That's all we know, right? Now, I want to consider all the cases. The first case is let's do like, what if AB is minus infinity to infinity? In that case, f inverse AB is what? Can this happen? So basically f goes from R to R, it goes to, this is R plus, right? So f actually goes from R to this R plus. It can be 0, but it cannot be negative. So what can you take f inverse of? You cannot go minus. Okay, so what are the possibilities of infinity? It can be some a to infinity or some a to b for a, b, real number. These are the two cases. So from a to infinity, what is f inverse of a to infinity? And these are real numbers, positive numbers, because there is no negative case. So there is a negative case, like, so if you are considering from R to R, okay, just imagine if you are considering from R to R, right? What if you take, for instance, minus 2 to minus 1? What is it? It's nothing but empty set, right? It could be anything. It's an empty set. These are the cases where it's empty set. Now what if f inverse of, what is f inverse of minus infinity to 1? So for these cases, what you do is, you can write it as a very simple example, separating this. For any a and b this works. For a and b in real numbers, right? For a and b in real numbers, we are doing this. These are the cases there. If a and b is less than 0, it's definitely an empty set. I have shown you this example. If a and b are both greater than 0, right? So this is f. So if this is the case, right? Sorry, 0 over here, right? If this is the case, so what is your set? This set, in this set, these are two open sets, union of, so it's either union of two open interval or phi, and when you have something like this, so just break it into two parts. For one, it's empty, And your union with empty is that set, so it's an open set in that case. Just this point, and these points can be infinity as well. So these are the only possibilities. So you can extend it to infinity as well. All these cases. Okay. So it's pretty simple, very simple question. Let's go to question 3. Okay. So f from R to R. So whenever function is given, it's very simple. Defined as very easy to draw plots and do these things whenever a function is given, especially in one dimensions, right? So at x is equal to 0, what is the case? At x is equal to 0, it's 1. At x going to infinity, something like this. Right? This plot, as you increase x, this number increases, so this always decreases. So f of r is contained in, is it an open set or a closed set? It's definitely contained in 0 and 1. So it is definitely bounded. Now for closed, for compact we need, so either these or these are true, or maybe it's an open set, right? So what is f of r? So we can clearly see f of r is nothing but this is true. We have already shown that f of r is this. We can also remove 1. Right? So, like, okay, let's start with this. Pick any point in f of r and we can show it's either between 0 or 1. Okay? Very simple. And 1, it's touching 1 definitely at 0. It's not touching 0. So that's why this is the case. So it's not compact because it's not closed. It's definitely not open as well. So f of r is 0. Very simple. Easy to always draw plot and check, right? Again, f from R to R satisfies intermediate property. What is this? If any AB belonging to f of r with f of x is equal to a, f of y is equal to b, and a is less than b, something like this, right? With f of this is a, and any c in R with a c b, something like this. There exists a z in R such that f of z is equal to c and or, so basically z lies between x and y. So now a function of R to R satisfies intermediate value property if and only if f is continuous. So when f is continuous, it's called intermediate value theorem. This implies intermediate value property. But the other way around is not true. For that, we give a counter example, f from R to R, such that f of x is sine of 1 by x in 0 when x not equal to 0. Symmetric function, definitely. Sorry, odd function. Right? It's something like this. After -1, it's something negative of something. It's an odd function and it goes to infinity, something like this. And this is minus n1. What is the graph of sine? Sine is something like this, right? And this value 1 pi by 2. So what is the value of pi by 2? Something greater than 1, 1.5. So 1 is over here. And it's definitely less than 1. So from 0, it's like a decreasing function. I'm not plotting it correctly, but yeah, there is no continuously going. And after that there are lots of oscillations in itself. So if you want, I can plot just 1 second. As you can see, after some point it's going like this. This is the case. Okay, a lot of oscillations. Okay, yeah, so is it satisfying? So like something like this, and then there is also something like this, and then yeah. How do we know that this satisfies intermediate value property? Okay, so this function is definitely continuous. So f of x is continuous on 0 to infinity and minus infinity to 0. So if you give any 2 points inside here or inside here, it satisfies intermediate value property. But what if they're opposite of each other? So so these x and y, so let's say pick any two a and b, and now f of r, no matter what, it's between 0 and 1. So like f of r is a subset of 0 and 1. minus 1 to 1. Subset of minus 1 to 1 minus anyway reaches 0. Yeah, it's a subset of minus 1 to 1. Okay. So you pick any point A and B, that's okay. But when x and y are over here, so there are x and y's, right? That is okay. But let's say when x and y are opposite to each other. So without loss in generality, let such that f of x is equal to a and f of y is equal to b. A, B belong to, it's actually equal. Not only there is a subset, they are actually equal. So A and B belong to. Now we have to show the intermediate value. Intermediate value property. Okay. So now just imagine that x is anywhere. So okay, there are two cases. This is one case. There is another case when A and B can be same, but x and y are not same. Oh, even A and B are not same for our case. We're just taking A and B different. For each A, there could be two x's and two y's. So we are just picking one of them. So one is the case when x and y's are like over here. That's fine. When x is 0, y is greater, and we can also do the opposite. And when this is the case, right? When this is the case, x is less than 0. Over here it is 0. And this is the case when there is x. This also implies over here. What we are doing is sine of 1 over x. So this definitely completes a cycle before this. Let's say x, so let's say x is equal to minus delta, okay, and so this space is delta. So it starts with sine of y is greater than equal to 0. Yeah, just remove this case. Let x, because x is negative, some delta, right? Sine of, just substitute over here, sine of minus 1 over delta is a. And b could be anything, doesn't matter what it is, but a and b belong to minus 1 to 1. Okay, so now if you want to plot this, so 0, there is a is Now this value could be anything. Okay, this value could be anything. It could be positive, it could be negative, we don't know. Okay, there is some delta over here. This is the value of sine 1 over delta. Now what I'm saying is that this completes an oscillation of 2 pi before 0. So as soon as it completes the oscillation, okay, so no matter what C you give between, okay, so C is between B and A, okay, and these are bounded by 1 and minus 1. It's covering all C between minus 1 and 1, so it's covering all C between A and B. So hence F satisfies intermediate value problem. Now if you want to see why this is discontinuous at 0, it's a little difficult to show discontinuity, but I'll try. So because for showing continuity, it's easy to say that for every epsilon there exists a delta, stuff like that, right? In this case, it's a little difficult. So for the, you have to do the opposite way. Okay, so you have to show that there exists an epsilon, such that for all delta, this is the case. Okay, so we have to show at 0. Okay, so what is f of x minus f of 0? Mod of that. It is nothing but sine 1 over x mod, because f of 0 is 0. So now we have to show that for all delta greater than 0, such that mod x is less than delta, this is the definition of discontinuity if you want to get into that. You have to show at least one epsilon greater than 0. For that, then we cannot show this. Such that for all delta greater than 0, no matter what delta you choose, irrespective of this, such that for all x inside delta, sine of 1x is greater than that epsilon. This we have to show. This is the opposite of continuity. So no matter what delta you choose, okay, and take any point inside it, so if I choose some delta over here, and when I do sine of 1 over x greater than equal to minus epsilon, So no matter what point I choose, I hope you are understanding that. So no matter what epsilon, this is actually not true for a single epsilon. No matter what epsilon I choose a very small epsilon, 0.00001. Okay, so let epsilon be 0.001. No matter what delta I choose, sine of 1 over mod x, right? So this is a delta, and I'm taking any point other than 0, obviously, inside this. Because there is no limiting process of this. If you take limit x tends to 0, this will go to sine of infinity. We don't know what that is. You understand? If a function, if you're defining it in two directions, there has to be a limit of this, right? And there is like a point like this, right? So from right hand side or left hand side, from anywhere, this is not defined, right? So for example, just take the right hand side limit, right? So and do sine of 1 over x. This is definitely, no matter what epsilon you choose, right, you cannot show this. Better way to do it will just take a limit x tends to, so just take a limit x tends to 0 plus sine 1 over x, not defined, and limit, and f of 0 is 0. This is not defined and this is 0. It's not even mismatch. It's not defined only. That's it. That is how you can do this case. So this is the example which satisfies intermediate value but not continuous, right? And to question 5. I hope you understand this. If you have any doubts, just let me know, okay? Sometimes it's in my head, maybe it's not able to convey it to you, so it's better for you to ask questions. So let f be such that f inverse of compact is compact for every compact set in R then f is continuous. We have shown that for every k, for every closed set, if that is there, then that is continuous. You have already seen this, right? But for compact, is it true or false? Okay, so like again, this whole section is about cubic counter examples. This I will do later. It's a big question. Okay, so show this. Let's do a very simple question first, because we want to like finish up all the questions and I want to finish up your doubts as well. Okay, question 8. Let Let A in R be non-empty set so that every bounded sequence in A is convergent. Which of the following is true? Okay. So we are talking about a set, and the solution is about what is if it's an interval or whatever. Oh, we're talking about interval, when it is interval, right? With positive length. I hope you understand what length is. If it's an interval, now A is singleton set, and then A is finite with size greater than 1. So when we talk about finite set, we talk about size is just a number of elements in it. Singleton means the size is 1. Finite, if there is finite set, what is the size? Number of elements in it. But that is not its length. Length is 0. Okay, so size and length are different things when talking about finite sets. Okay, so it's a non-empty set so that every bounded sequence in A is convergent. So A in R is non-empty first of all. Such that every bounded sequence in A is convergent. So let A and B belong to it. So either it's singleton or it has 2 elements, at least 2. So let's say A and B belongs to it. This does not mean I'm assuming it's finite, it's interval, no. Let 2 elements belong to it. With A not equal to B, right? 2 elements in that, right? Now define when n is odd, is the sequence bounded? Xn is definitely bounded by max of A and B for all n, but not convergent. Hence, A cannot have 2 distinct elements. So whenever you have a set, every bounded sequence is convergent. You cannot have that set basically. You can only have a singleton set. Okay. This is question 7. Okay, it's again a true and false question. Let f from A to B to R be uniformly continuous. Yeah. Then there exists G from A to B. Now it's defined on a closed interval to R such that G is uniformly continuous on and G is equal to F on EB. This is called the extension problem. So you have an F which is uniformly continuous, you define on A and B, something like this. What you are saying is, I want to extend this in a very unique way, such that the G retains the uniform continuous property. There could be many extensions. I can extend it like this, that is not even continuous. I don't want to just retain continuity. We want to say that it's uniformly continuity is retained. Okay, so what we do is, so let's say F is defined from AB to R. Okay, what we will show is that limit exist, and then what we do is we define G as f of x we have to just show one of them, the other one follows. This is how we do it, right? And clearly G is equal to F on A to B. Now uniform continuity, how do we show? So for uniform, I will show this later, but first how do we show uniform continuity? So for any x and y between A and B, that is fine, but if one of them is over here, that is the problem, right? So now you have to show that x minus A then delta implies f of x minus f of A, G of A Now, this is the case where how do we define this limit, right? Limit of extend to this. So this is we define in the sense that every epsilon greater than 0 there exists a delta such that we're defining in terms of f, right? This is the case. Let's call it epsilon 1. Let's call this y, sorry. We have to show this. We have to show. But what we know for this case, okay, x is definitely less than a, right? Greater than a. Extendment. Okay, so one second. This is a, this is b. A plus delta and a. This is the case. Right? And x is greater than delta. So for every x, and x is not equal to a as well. So but over here the delta depends on this epsilon 1 and a. So it basically depends on just epsilon 1 because a is given. It doesn't depend on x per se. Also, since x and y are out inside this, since f was continuous, this also implies that x minus y bounded by some delta prime okay. So this is given, these all implies that xa to a plus d, and when you sum this up, f of x minus f of a, or rather there is g of is the limit point. So from this, if you sum it up, what you get is f of x minus g of a. And f and g are same when x is this, so this is nothing but g of a is bounded by epsilon prime plus epsilon 1. Call this epsilon and you are done. Call this delta, call this epsilon. Okay, so it's easy to show that uniform continuity same goes the other way around. Okay, you can show for any point in x. So you have shown that for any point x and y, which is bounded by delta, this is the case. Okay, so now all you have to show is that this limit exists. Only one of them, it's required to show only one of them. The other one will follow. Okay, so we have to show that limit extending to a plus f of x exists. That's all we have to show, and f is uniformly continuous. You can easily give g. Okay, and it does exist. Because of uniform continuity. Even with continuity you can show, but we will use uniform continuity if this exists. Okay, so consider a sequence like this. This implies that xn is Cauchy. So there exists n naught in z plus such that nm greater than n naught xn minus xm for any delta greater than 0. Now for every epsilon, this delta I will fix. For every epsilon greater than 0, there exists a delta greater than 0 such that x minus y bounded by delta implies f of x minus f of y bounded by epsilon. Choose delta star to be delta. That implies f of xn minus f of xm is bounded by epsilon for all nmn greater than n naught. Hence, f of xn is Cauchy. Okay, so hence it converges. Let's call this limit like this. Okay, now let yn in A and B such that yn converges to A. Okay, hence that implies f of yn limit also converges to some value L prime. By continuity, because f is continuous as well, right? We can take limit inside. So basically f of, so this will, what this will be called is, we have to show that f of a is not defined. Yeah, so f of a, see, f is defined only on the open set. Okay, f of a is not defined. So now let yn converges to A and f of 4 converges to this. Okay, now define z of n as xn when n is odd and yn when n is even. So over here, initially what we had was xn converges to A and yn converges to A. There are two values which are converging to A, xn and yn, these are zf. Okay, and they both converge to A. So there are two sequences, both are converging to A. What can we say? So for existence, what do you need? That any sequence, basically we can say this is a limit of what do you say? We can conclude that if L was equal to L prime, we can say that if basically L equal to L prime, we can say because we have converted it into a sequence, right? X. So instead of xn and xn going to n going to infinity. So this, what does it mean to define? We can call this a limit of, because these both things have to be same. It has to be unique. Because when you want to say limit exists, it has to be unique. You cannot have two values. Okay. Now if you write f of zn, but f of zn, basically zn also converges to a, right? So for it to converge, every subsequence has to converge. So if this converges to, you cannot converge to two things from here. So the limit is basically, no matter what sequence you choose, the limit is the same. That's why we can say that this converges. So there's a lot of questions about uniform continuity. I'll do one more and we'll call it a day. It's a true and false question. Continuous and periodic. And f is uniformly continuous. For example, sin x function and stuff like cos x. Is that continuous and periodic? Okay. So let there will be some period. This is the periodicity. Can we say f is uniformly continuous from 0 to p? So since f is continuous, let's check let xy belong to 0 to p. Okay. And f is continuous, right? So for every epsilon greater than 0, there exists a delta dependent on epsilon and x, such that for all y with y minus x less than delta implies f of y minus f of x this delta basically depends on epsilon and x. But this delta depends on epsilon and x. X could be something between 0 and p. It's a compact set. So for each of them, there is a delta. Says that this is true. Is delta continuous? Since f is continuous, the delta on x is continuous. Hence, and x is compact, hence f is delta epsilon of x can be replaced with delta of epsilon. Okay, so that implies f is uniformly continuous on 0 to p. Because of the continuity. So now you can write R as closed sets, and in each of them it's uniformly continuous. The whole point of uniform continuity is on the boundary what happens. Okay, so we take delta to be minimum of delta and p, but you will see how it comes. Now consider any, now for any x and y in R and y such that okay, so since delta is just minimum of delta p by 2 and delta is definitely a smaller quantity than p, that implies that x belong to xy both belongs to some case, or there is a difference because we have taken x y greater than x. So this is in this and y is in the neighboring thing. So when this is the case, we have already shown it's uniformly continuous. That is done. Only this case remains. Okay. So for here, we have to define that x prime is equal to x minus np and y prime is equal to y minus n plus 1p. This will imply that x prime, y prime belongs to 0 to p. Okay. Also, x prime minus y prime and x minus y, we take the max of it and then bounded by delta prime. You can choose this. So f of x prime minus f of y prime is bounded by epsilon and by periodicity. F of x minus f of y is bounded by epsilon. Question 5, I'll give you some hints. Maybe we'll do it in next class or something like that. So there is an example that f inverse of k compact for every compact set in f is continuous. So you have to show that for every compact set, this is compact. So the counterexample is f of x is equal to x plus 1 of x. So you have to like 1 point discontinuity. You already seen how that works in sine of 1 over x case. So if you take x, limit x tends to 0, this is not continuous. So not continuous at x is equal to 0. Now you have to take a compact set. The compact interval is a very different thing than compact set itself. Okay, and just 1 second. Compact set is very different than compact interval. It's a little tricky. There is solution is already uploaded. I'll just give you a hint through how to go through that. So we're talking about whenever x plus 1 over x is equal to a, we are talking about real numbers over here. Only valid solution when a square greater than 4 or mod a greater than equal to 2. So what is this range of f? I hope this is clear. And f of 0 is 0 only when it's 0. Okay. It is easy to see for any interval. Say if you just check any interval in here or in here, as in take any interval because it's compact set in 2 to infinity. clearly this implies that f inverse of, you have to use the quadratic equation, is nothing but we are using that Sri Bhattacharya formula of a minus under root a square minus 4 over 2 union, again a plus under root a square minus 4 over 2 and b plus under root b square minus 4 over 2. Similarly the other way around. So what you are doing essentially is, so for any compact set, interval inside minus infinity to 2 or 2 to infinity, these are compact intervals, so hence compact set is compact. Okay, so now let K be an arbitrary compact set. So we can say K minus is K interval minus infinity to minus 2, minus 2, let me write minus 2 everywhere, yeah, and K plus B, K intersection 2 to infinity. So we have already shown that K plus and K minus are compact, right? Because it's a compact set inside minus 2 to infinity, so it could be anything in form of A and B inside, nothing else. Okay. Okay. The same idea now, f is continuous except x is equal to 0. It is continuous, right? So now if there is a compact set, arbitrary compact set, probably it contains 0 or it does not contain 0. If it does not contain 0, right? If 0 does not belong to the compact set, okay, so it is a compact set and 0 is not there, and f is indeed continuous over there, then it is definitely compact. But only problem is when 0 is involved. Okay, a compact set where 0 is involved. Continuity of but there are only 3 ranges, so no matter what compact set you choose, okay, it will be bounded by some minus d to d, some minus delta to delta, it will be inside that. Okay, so now let's take the compact set intersection with the range of R. So K is equal to so if we take f inverse of K, again inverse respects this union, this is empty set, so that's gone. So all you have is K intersection range of f. Range of f are these. So if K is intersection with this, again I have shown this is compact, this is compact. K intersection with other thing is only 0. So this is nothing but 0 union some compact set, which is compact because 0 is also compact. Union of two compact sets compact. I think that is how you can do this. Yeah. Kartikeya, go ahead and ask your questions. Week 7, just 1 second. Yeah. Assignment number 7, right? Yeah, which question? Four, okay. Okay. So let's say you have PK, right? P1, P2, P3, P4, so on, right? These are all partitions, yeah. So this is PK, right? You understand this? PK square is nothing but P1, P4, P9, P16. It's a subsequence. And PK cube is P1, P8, P27, something like that. So what they're saying is that U of, if you're doing partition like this, you take the upper bound of F and then you take the lower bound on key cube and then the limit is 0, then is F Riemann integrable. No. Upper sum of this minus lower sum of this and then you take the limit. It may not, so you understand this, right? Limit n tends to infinity an plus bn or an minus bn, right? Whenever this exists, this does not imply that limit an minus limit bn. Not always. They both have to exist. You understand this, right? Because you have not shown f is Riemann integrable yet. All you have shown is that the limit of an minus bn is 0. Yeah. So I hope you get this. So do you have any questions in assignment? What was this? 5. Yeah. 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 Okay. That comes to practice. Okay, I will tell you something. Always go with the counter examples. Okay, so whenever f is continuous, right? Can I extend this? Okay, to make the whole function continuous. you understand my point? Let f be defined from A to B, and f is continuous. Do you think this is always true? Are you there? So, those who are watching over here, there's an example in the assignment itself. Take anyone, like sine 1 over x or x plus 1 over x. These are continuous. At x positive, these are continuous. So f is continuous from. Oh, you came back. Hi. Yeah. So what I'm saying, let f be defined from AB to R, and let f be continuous. Do you think this is always true? Yes. From the right hand side only, because it's defined only on AB. Yes. And f is continuous. Not uniformly continuous, just continuous. No. F is continuous. Can you? It is not defined on A. It is defined on this open interval. Can you say that this limit exists? Yeah. So the counter example is in this section only, like sine 1 over x. It's continuous from 0 to 1. F is defined and continuous on the open set. Let's cut everything. I define the same f from 0 to 1 to R, right? I can call it f of x to be sine of 1x, right? Now I am asking limit x tending to 0 plus f of x. Does this exist? No, right? Why? It is bounded only. It is if sine of 1 over x is between minus 1 to 1, but it is oscillating. For the case of x plus 1 over x, which we did in question 5, over here it's unbounded. Over here it's oscillation. So just continuity is not enough to extend your functions. That's why you need uniform continuous. That's why for uniform continuity this is true. If f was just continuous, this need not be true. For uniform continuity, it will exist. That's what we are showing. that I have shown already, that it is continuous. It is not the case for just continuous. That's why uniform continuity is important. Whenever a condition is given, you have to think about why it is important. Like why are we talking about, like when you see this question, you can say okay, f is continuous. You can always extend it by, like, for any simple function, right? Something like this, you can always extend it. But at the border, at the corner, the function is fluctuating like this. It loses uniform continuity and loses the existence of the limit on the boundary. Okay, so you have to, whenever there is oscillation or it's going beyond something, it loses the whole, like, how do you say, the uniform continuity, and in turn this existence of limit. You cannot show the existence, you cannot extend it. But if it's uniform continuous, you can extend it. So this is, the counter example is in, was in the solution itself, like if you think like this. So yeah, for counter example it's difficult, I can understand, but you have to think about how, so you've learned about unboundedness, boundedness, oscillations. These are the two things, right? With oscillations, there are two ways in which the limit is not defined. If it goes unbounded or if there is oscillation. Like for example, sin x and x. At x tends to infinity, both the limit does not exist. These are only two cases that happens. Or it could be both unbounded and oscillation. Like just imagine sin x, turn it with, like just rotate sin x in such a way that it's oscillating over x. So it could be oscillations and unboundedness. But if it is bounded, so there has to be oscillations. Not periodic oscillation, not necessarily. It could be any kind of oscillations. So these things have to be kept in mind. Slowly you will get this. Okay. So yeah. So I'll finish the class today.